Okay. So this is the physics day of the conference, but now we get almost into chemistry, but looking at it, it's Bott periodicity more than Mendeleev. Next speaker is Zirnbauer, and the title is Bott periodicity in the periodic table of topological insulators and superconductors. And I don't know how to get the projector going. Projector?
Yes. Has to warm up, I guess.
Warming up. So,
Okay, so I'm thankful to Alan Carey for asking me over. It was only a short trip for me since Cologne is next door. For 10 years I've been in Bonn very regularly as vice chair and then chair of the Bonn Cologne Graduate School. So I feel at home, and it won't be exactly chemistry, but somewhere between mathematics and chemistry, which is physics, theoretical physics. So here is the table that the talk will be centered around. This table was first put up. There should be a laser pointer here, but there is not. Okay, so that's bad news. Then I use my own. Oh, did I make a mistake here? It seems to be low battery or something. Sorry about this. So this one certainly could also have low battery, but okay. So I'm gonna go this way. So Alexei Kitaev put this up. I think I first saw it in June 2008. What you see here are K groups, more precisely something like twisted equivariant K groups, over the d-dimensional sphere with a non-trivial involution. And the sphere is the momentum sphere, and the involution is momentum inversion, k to minus k. And the vector bundles are subject to some symmetries. We'll speak about this. All of these things will be explained. And these symmetries are such that one can use Cartan's notation for the large families of symmetric spaces as a label. This table, I would say, caused quite a stir in the condensed matter community. In any case, it's been shown in many talks and reproduced in many papers. Here I've taken the review by Hassan and Kane. What the table does is it unifies a number of things that were known in 2008. The story of topological insulators and superconductors starts, say, in 2005, if not in 1980, which is when the quantum Hall effect was experimentally discovered. But not only does it unify information known at that time, it also predicts some interesting topological phenomena that have not been discovered hitherto. All right. So, talk is in 3 parts. Hopefully, I'll be done after 45 minutes. In the first part, I will present the mathematical model that gives rise to this table. In the second part, I want to give a little bit of credit two people who contributed to the historical development. I'll give you one example, and in the final part, time permitting, I will say a few things about work we've done in Cologne, beyond the formulation of the model up here. Okay, first part, the mathematical model. I will assume translation invariance. I should say right away that this is not for the long term. What one really would like is a theory that handles disorder. And this theory is beginning to emerge, but I have not contributed to it. It's an evolving story. Here in this talk today, translations are symmetries. That means that we have Bloch theory, the theory of Bloch bands at our disposal. Momentum is conserved, so we'll be speaking about vector bundles over momentum space. The notation is standard notation of physics. We are in, this is a theory of many particle ground states, and we have Fock space. There are operators creating a particle and operators annihilating one, and when momentum is conserved, it makes sense to label them by the momentum. Now, the first important fact is that so-called free-fermion ground states, also known as ground states in the Hartree-Fock-Bogoliubov mean field approximation, are completely determined by saying for each momentum which are the generalized annihilation operators, so-called quasi-particle annihilation operators, which applied to the ground state gives 0. In other words, there's a one-to-one correspondence between the ground states of the physics of interest and collections of vector spaces A sub k. K runs through the momentum space, and each vector space is a space of linear combinations of the generalized annihilation operators. Example, let's assume that charge or particle number is conserved. Then, and let's say there are two bands, one conduction band, or P as in particle, and one valence band, or hole, or H as in hole. Then this space will be two-dimensional. Conduction bands, by definition, are empty in the ground state. So when we apply the standard annihilation operator, we get 0. There's no particle to annihilate. The valence states are filled. This is sort of a Fermi sea, filling the states up to the Fermi energy. The valence states are filled. When we try to create another particle, the Pauli principle says this is going to be 0 by the antisymmetry or the algebraic structure of Fermi. So that's an example. Now, it's important that this is a story about insulators. If the physical system were a metal, the dependence of this annihilation space on momentum would have a discontinuity at the Fermi surface. And there would be a jump. And then the story ends here. However, since the focus is on insulators, where we have a gap everywhere separating the valence bands from the conduction bands, this dependence actually continues. So it gives us a vector bundle. Continuous dependence on K, or even smooth dependence on K. So we have a vector bundle of these annihilation spaces over a momentum space. Now, even, another important point is this one, even if there are no symmetries whatsoever beyond translations, which are needed, otherwise we don't have the setting of Bloch bands, even if there are no symmetries other than translations, there's still a condition which is to be satisfied by these spaces. It's the condition that you have on annihilation operators in the formalism of second quantization. these operators all together form a Clifford algebra, the annihilation operators amongst themselves should form a Grassmann algebra. They should all anti-commute. So if these are truly annihilation operators, they better all anti-commute with each other. So they annihilate, these spaces annihilate with each other with respect to the anti-commutator bracket. So far, no symmetries other than in translations. Now let's build symmetries into the model. And that makes it rich and interesting. In the process, as outlined by Kitaev, physical symmetries will get transcribed into pseudosymmetries. Let me tell you about the outcome first and then explain afterwards how this works. So for a system of symmetry index S, there's a Clifford algebra of S pseudosymmetries, each given by a complex linear operator J. There are Clifford algebra relations. And where do these act? Well, on the sum of these annihilation spaces together with the corresponding creation spaces. Because we're now taking all of the operators, the sum is actually independent of K. Now, okay, so I'll distinguish between right and left here. This is a challenge to the brain. So here's a definition. If you don't understand anything about this talk, at least you should be able to take away this definition. I'm saying this: a translation invariant ground state, free-fermion ground state of a gapped system of symmetry class S is the following. That's the object to study then for a mathematician. It is a complex vector bundle. More precisely, it's a sub-bundle. So there's a total space. There's a trivial vector bundle of momentum space with constant fiber of dimension 2n. What we are studying are fibers of half the dimension, so rank n sub-bundles. And these fibers are subject to conditions. We've seen the Fermi constraint. We have understood what's the physics of that. Now, in addition, there are pseudosymmetries. So applying any one of these generators of the Clifford algebra of pseudosymmetries to the vector space of annihilation operators, we should get the vector space of creation operators. That's why these are called pseudosymmetries. A true unitary symmetry should take an annihilation operator and transform it into another annihilation operator. These operators do something bizarre. They take annihilation operators into creation operators, so when acting on the ground state, they produce a very highly excited state. Therefore, I very strongly hesitate to call them symmetries. They're not symmetries in a good physical sense. We'll call them pseudosymmetries. And now comes an important point. Every one of these pseudosymmetries, when you set things up right, comes from a true physical symmetry. Let me explain that in one instance. Let's say time reversal is a symmetry. If so, applying the time reversal operator to any annihilation operator at momentum k, I should get an annihilation operator at momentum minus k. That's just a statement of symmetry of the ground state. Now, let gamma be the operation of Hermitian conjugation in Fock space, swapping annihilation and creation operators. Then composing T with this gamma, what we get is an operator. Well, so we've gone to k to minus k. If we now take the Hermitian conjugate, we go from annihilation to creation. We go back from minus k to plus k. So actually, we end up here. So J1, using this symmetry condition, J1 actually does its pseudosymmetry job. It takes AK and transforms it into its orthogonal complement. So here's one instance of how a true physical symmetry gives rise to a pseudosymmetry. This is not an isolated instance. This turns out to be systematic. And it was first understood by Kitaev and written down in part by him. So the first step, so we can start with no symmetries other than translations. then we still have this Fermi constraint. Then we add time reversal symmetry as just shown. That gives us one pseudosymmetry. One thing I didn't say is that when you square this, you actually get -1 because by definition T is not any time reversal operator. I should have said this. This is time reversal for spin 1/2 particles, in which case the square is -1. This property gets transferred to J1 having also square -1. So that's the first generator of this Clifford algebra of pseudosymmetries. Now we can continue. For the next true physical symmetry, we add charge conservation. So that the U1 group behind it, or the generator, or thereof, the charge. This allows us to form a second operator, J2. You easily check, using the physical properties of these, that J1 and J2 anti-commute. And J2 also, this was forced by putting in the right factors, J2 also squares to -1. And the fact that Q is a symmetry, by a similar calculation as the one shown before, translates into the fact that J2 is a pseudosymmetry. And this keeps on, and one can continue this. So in the next step, we add an operation called particle-hole conjugation. And now that's a true symmetry. And I look at Hermann Schulz-Balders. This is not something that anti-commutes with the Hamiltonian. It commutes with the Hamiltonian. Yeah? So it's a true physical symmetry. You can use this particle-hole conjugation operator, which you see it's complex antilinear together. So one thing I didn't emphasize also here, that T is complex antilinear. Hermitian conjugation is complex antilinear. So these J's are complex linear, as they should be. Same thing for the J3. It's complex antilinear. It anti-commutes with the other ones. It squares to -1. So here we have our Clifford algebra of pseudosymmetries at level 3. To continue, we have to wipe the plate clean. So we cross out all of this, and we start anew. We now declare that our physical system, which we really talk in condensed matter applications, we're talking about electrons with spin 1/2. And electrons carries the fundamental representation of SU2. S1, 2, 3 are the generators of SU2. And if spin is conserved, because spin rotations are symmetries, then these are the generators of true physical symmetries of our system. In a moment, I shall explain that this situation is equivalent to having 4 pseudosymmetries. And then one can do a repeat of this story. You include T, time reversal, charge conservation, particle-hole conjugation, and this takes you all the way down this list of 8 entries. So the thing that needs explanation, and to my knowledge, was not explained in the literature. In a Cologne paper that we recently published, this is filled in. How does this go? Why do 3 spin generators amount to 4 pseudosymmetries? Now for this, we need a tool called 1-1 periodicity. Here's some notation. Let C sub S denote the so-called classifying space for class S. That's the space of solutions. These are these vector spaces. The vector spaces that solve these pseudosymmetry conditions. That applying these complex linear operators, we get the orthogonal complement. Here I'm dropping the K dependence for the moment. Yeah? Inside these complex classifying spaces, there's a quote, real unquote classifying space. That's the subspace where not only the pseudosymmetry is solved, but also the Fermi constraint is satisfied. Now what we do is the following. We double the number of bands. In the double space, so we start with a system with S pseudosymmetries. And in the double space, we put the original generators on the off-diagonal blocks. And we invent 2 new generators, just like this. Okay? Then you check that all of these give you a new Clifford algebra with 2 extra generators on the double space. And there's only one subtlety. The generator K, so there's one thing I didn't emphasize. These J's are not only complex linear, they are also unitary operators of the Hermitian structure here, and they preserve the anticommutative bracket. So they are orthogonal with respect to the curly bracket, and they are unitary with respect to the Hermitian scalar product. This one fails to be orthogonal. It reverses the sign of the bracket. Notice that I could have made a different choice. I could have left out the I. Then it would have preserved this, but then it would have squared to +1. I like it better this way because some of the formulas look more uniform, but it's equivalent. Anyway, in this setting, there's a well-known result. It's that things remain unchanged. So we doubled the number of bands. We increased 2 generators. It's important that one of them, the I, is sort of, say, a real generator, and the K is an imaginary generator. That's what this 1, 1 here is supposed to communicate. And if so, the situation remains the same. These classifying spaces are in bijection. So there's a canonical bijection taking one to the other. So using this, we can answer this question of why 3 spin rotation symmetries are equivalent to S minus 4 pseudosymmetries, and goes as follows. So let there be some pseudosymmetries, say S minus 4. And in addition, let there be the 3 spin rotation symmetries. So these are pseudosymmetries. The spin rotations are true physical symmetries that are applying any of the S's to the A sub k. we reproduce A sub k. It's the annihilation space is invariant, while these, I emphasize this, take the annihilation space and turns it into its orthogonal complement. Okay, so that's the setting. Now we do this doubling. As before, we put the pseudosymmetries on the off diagonal. We put the physical symmetries on the diagonal. We make some identification. We observe that pseudosymmetries commute with symmetries. That's physical input, which I'm not showing here. Using that input, you verify that all of these operators together, that the J tilde, starting with 1 and ending at JS, they form a Clifford algebra. All of them square to -1, so with negative signature. And now by an easy argument using the 1-1 periodicity lemma, you arrive at the desired statement, namely that 3 spin rotation symmetries are exactly equivalent to S minus 4 pseudosymmetries. So that explains sort of the systematics of Kitaev's table, and we're beginning to see Bott periodicity. These spaces C sub S and R sub S, which I showed before, are well understood. And here's what they are. I didn't tell before, but these guys up here are exactly that. These are these well-known symmetric spaces put in this very order by Bott for a certain reason. From the perspective of condensed matter theory, sort of the important message here is that the symmetries that one is familiar with and that one wants to use and impose in the context of electrons in solids, here in particular in insulators, these symmetries, when you organize them in the way that I just showed, give you another rationale for this ordering. Yeah? So Bott has a reason for ordering them like this, and I just gave you another reason to put these spaces in exactly this order. I said, add physical symmetries in a certain order, show or work out that they translate into pseudosymmetries and get exactly this sequence. Now, why did Bott put them in this order? Well, his observation was that if you go to anyone, it's the same up here as down there, so focus on any one of these spaces and then ask, and then look at the space of minimal geodesics taking you from pole to antipode, say here. He observed that the space of minimal geodesics from pole to antipode in this space is parameterized by the points of the next space. The next space is actually a subspace, and you could imagine this being the equator of this bigger spherical space. Yeah? And then using Morse theory, he showed that the space of minimal geodesics is a good model for the loop space in low dimension. It breaks down in high dimension, but in low dimension, the space of minimal geodesics is a good model for the loop space. And then by trivial identities of homotopy theory, you get that homotopy groups, as long as you are in a stable range, so as long as the minimal geodesic model captures the loop space model correctly, as long as in a stable range, you have constancy of these homotopy groups. Now, the Kitaev table has constancy this way. So that, for me anyway, and I think for some other people, some 4 or 5 years ago, was the puzzling thing. So Bott periodicity means things are constant this way, but Kitaev says, well, in this physics of topological insulators and superconductors, things are constant that way. So that needs to be explained. And here I'm giving you some historical credit to authors that contributed to this story. Story starts, well, topological insulators and superconductors start in 2005, and there are thousands of papers. Here I'm just focusing on that little sector of this activity that led to the periodic table. So that starts in Santa Barbara, in California. A group of postdocs around Andreas Ludwig were studying Anderson localization on disordered surfaces with topological insulators, and it discovered interesting phenomena, which then were put into a systematic picture by Kitaev. He understood the relevance of symmetries or pseudosymmetries in giving you a Clifford algebra, and he understood that Bott periodicity of complex and real K theory was in some way or another behind this. Theo and Kane pointed out that if you, there was an extension of this story, which includes defects in position space. There was a paper from Illinois which sort of gave a tutorial to the physicists, drawing physicists' attention to work by Atiyah, Bott, and Shapiro on Clifford algebras and how they organize and are classified. And in particular, that Bott has this, or as nicely written in the book by Milner, that you should put symmetric spaces in this prescribed sequence that we saw earlier. There's a paper by many authors, again with center in Santa Barbara, where so ideas, general principles are there, but I don't think there's any real theorem or proof as far as I can see. The existence of a proof is mentioned here, assuming that every Hamiltonian that arises in this condensed matter context, and which will have for its ground state one of these objects that we've been looking at, assuming that every one of them is homotopic to a Dirac operator, then this paper gives you proof of the table. If you look up where is it proved that every Hamiltonian is equivalent, is homotopic to a Dirac operator, then it says Kitaev unpublished note, as far as I know. Maybe there are now I may not be totally up to date, but that's what it says in that paper. A very important paper is that by Fried and Moore. It's about 100 pages. And the title is Twisted Equivariant Matter. So they develop twisted equivariant K-theory. And they don't formulate quite that model that I gave to you. They do something slightly different. It's equivalent. I do prefer the formulation that I gave. So that is why I have given you, because as a physicist, I think it's better motivated. But what they do is mathematically equivalent, so you can use it, and you can compute the K-groups and then fill in the entries of the table. Last but not least, I should mention that this is still using Bloch band theory. Momentum is conserved. We're dealing with vector bundles over momentum space or groupoids. What one really would like to develop in the mid or long term is the version, the disordered theory. And this is beginning to emerge, mostly due to work by Schulz-Balders, Podan, and a few others. Okay. Now I want to give an example. And the example is in 2 dimensions. And it's called class A2. The name is the quantum spin Hall insulator, which is realized physically in a sandwich where the important player is mercury telluride. So this is a material long known and long studied, and it was realized there's something very interesting about this. And now let me sort of put this into this framework. In this case, we have 2 physical symmetries. The U1 symmetry behind charge conservation, or its generator Q, the charge operator, and time reversal, squaring to -1. That's labeled by A2, but in physics language, that's the symmetry setting where the quantum spin Hall effect takes place. Now, in this setting, one can actually do a reduction. It's not necessary to work with the full generality of these annihilation spaces A sub k. You can actually eliminate this Fermi constraint by also eliminating this symmetry. The 2 of them somehow together go down the wash, and you're just left with the anti-unity symmetry given by T, which now acts on this on a reduction of these A spaces called V. And the physical symmetry means that time reversal applied to the fiber. This is the space of valence states, V as in valence or vector, if you prefer. So time reversal applied to the vector space of valence states at K should give you the vector space of valence states at -K. That's a statement of symmetry. At K invariant momenta, on a torus, this momentum inversion condition has more than 1 or even more than 2 solutions. It has twice as many solutions as the number of dimensions. So for time reversal or T invariant momenta, T has to stabilize this space. Now, the mathematical task now is to classify vector bundles of this type. This is a vector bundle, a real vector bundle in the sense of Artia. You have a involution on the base, momentum inversion, and you have an involution. Well, not quite. It's an involution that squares to -1. So it's a quaternion vector bundle. Not quite of the type envisaged by Artia, but very close. How do you do the diagnostics? How do you find out whether the claim is that these vector bundles fall in 2 classes. How do you do the diagnostic to tell whether you are in a trivial or in a non-trivial class? Well, here's how it goes. We have this T operator. We use it together with the Hermitian scalar product. We use it to produce a map from V to its dual. because t squares to -1, you verify that this map is skew-symmetric. So there's a Pfaffian. Let the Pfaffian at k be p of k. This Pfaffian cannot vanish at a t-invariant momentum because the symmetry condition, t applied on v of k, giving again v of k, means that this map is symplectic at such momentum. So Pfaffian is not 0 so in the simplest case, we have two t-invariant momenta, namely 0 and infinity. Cannot vanish here or there. Other than that, zeros occur in pairs. From the algebraic properties of t, you derive that the complex conjugate of this Pfaffian is the Pfaffian at -k. So zeros always have opposite zeros. And zeros can be created, and they can annihilate. For example, this 0 can annihilate that 0. They can merge and disappear. But then also this one disappears. They cannot disappear at 0 at infinity because of this condition. The bottom line is zeros appear or disappear as quadruples. So the number of zeros is well-defined. It's always even, and it's well-defined modulo 4. That means you have a Z2 classification. So there is either an odd number of zeros or an even number of zeros. The interesting case is an odd number of zeros, the elementary case being 2 zeros, say this one and that one. So that is a simple representative of the quantum spin Hall insulator. The experimentalists don't care much about this. What matters for experimentalists is that by a principle called the bulk boundary correspondence, the existence of, or the non-triviality of that invariant forces a similar phenomenon as in the quantum Hall effect, namely you have perfectly conducting surface modes. Unlike the quantum Hall effect, they are not chiral, they're not directed. You have modes, one mode going in either direction at the boundary. And the consequence of this is that in experiments, you see a conductor. So this is a prediction, and it's been verified in experiment. You see that the conductance actually is 2 in the fundamental unit. It's counting the 2 surface states. So that's a wonderful story, and it seems to me there's some consensus or some feeling in the condensed matter community that the prediction of this phenomenon experimental verification is beginning to border on the level of achievement that deserves a Nobel Prize. You know? But the Nobel Prize hasn't been given yet. So the last, I guess I have 7 minutes, yeah, will be sort of what did we do in Cologne about all of this? In particular, so if I don't get to the end, the message is that if you know what Bott did, or what the mapping was, sort of this idea of considering minimal geodesics between pole and antipode in a symmetric space, and this being parameterized by a symmetric subspace, and the whole thing being a good approximation in low dimension to the loop space, in some sense, the square root of this map is the one that you need for the Kitaev table. So that's the message. So here, pictorially. So Bott goes this way, constancy. Kitaev says no. The Santa Barbara group say no, it's like this. And Kitaev says, well, the K groups, when we compute them, are like this. The K-theory computes these entries individually, at least in my understanding. And so the question arises, is there a map between these? Is there some isomorphism here? Yeah? So, yes, there is. Call it the diagonal map, and it works as follows. What we want to do is we want to go up in dimension by 1, and at the same time increase the symmetry index. Yeah? So go up in dimension, and get down in this sequence where we increase the number of pseudosymmetries as we go down. How does this go? Well, so we start here with S pseudosymmetries and a vector bundle solving the pseudosymmetric constraints, and those are the Fermi constraint in d dimensions. Now, we can use this, we can put to good use this 1-1 periodicity. We add two generators. We double the space, so n bands become 2 n bands. And we lift the vector bundle to the double space. And the bottom line is we haven't changed anything. You know, we've increased the number of Clifford algebra generators. We've increased the space. But that means that the space where this moves is exactly the same. So we've just reformulated the starting point. And now we add one dimension by doing what Bott does, and what's nicely explained in the book by Milner. We come up with a one-parameter group. So T, this coordinate T, this parameter T is going to be the coordinate of the extra dimension. We cook up a one-parameter group and then make these fibers variable, and thereby produce a vector bundle in one extra dimension by this expression. So J depends on A. It multiplies by I on subspace A and by minus I on the orthogonal complement. And now you do a little computation and verify that this has all the desired properties. First of all, the variable fiber satisfies this kind of a dimension extended Fermi constraint. That's good. The variable fiber satisfies the old pseudosymmetries that we started with, plus a new pseudosymmetry that comes from this generator which we invented by using 1-1 periodicity. And the third point is that the fiber at t equal to plus or minus a half degenerates. It becomes the eigenspace of the imaginary pseudosymmetry with eigenvalue minus 1 or plus 1. So what that means is that starting with a vector bundle in d dimensions and S symmetries, we've produced a new vector bundle with an extra symmetry given by the extra pseudosymmetry I. And in one extra dimension, because of this degeneration, what we've really done is we've suspended the original momentum space in one higher dimension. And the suspension is the one, as you can see from here, suspension is the where the involution acting on momentum space is extended non-trivially, therefore the tilde. Okay? I'm going to skip this because my time is up, and it's really more intended for a physics audience. I have a couple of examples where this diagonal map is illustrated. You can start using physics language from the Majorana chain and go to a one-dimensional topological superconductor with spin triplet pairing and T invariance. Using some physics notation, one can explain this, and it works out very nicely. One can go one further step, starting with this 1D topological superconductor. You can add one step and go to the quantum spin Hall insulator that I used for illustration. So all this works very nicely. One can continue and go to 3D, class C2, and one can go to 4D, class C. That's something Hermann and I talked about during the coffee break this morning. Okay, I'm getting at my sort of final slide with result. This is an easy transparency, which is just to say that we now switch language. We switch language from vector bundles with fibers constrained by S pseudosymmetries, giving a Clifford algebra. We go to the corresponding classifying map by simply saying that for every momentum, we have such a fiber. So let's make this assignment. Then what we get is a map from M into the classifying space. There is also the Fermi constraint. We can reformulate it like this. And on the other side, the classifying map side, it becomes a condition of Z2 equivariance on phi. So phi k perp, the perp operation being the one, still the orthogonal complement with respect to the curly bracket. Phi k perp has to be phi minus k. In this language, the diagonal map takes a classifying map defined on momentum space M, going into the classifying space with S pseudosymmetries, Z2 equivariant, and also base point preserving. This is a technical detail. It adds one dimension, it adds one symmetry, and it doubles the number of bands. That's what it does. And we have proved that this is actually a bijection. Provided that M satisfies some technical condition, it has to be path connected, but more importantly, it has to be a CW complex. That's rather, we are rather happy with this because that's a rather weak assumption. More important is that we have to be in low dimension. The dimension of M has to be much smaller than the number of bands. Remark number one, the S tilde is the momentum type, the non-trivial suspension, where the operation of momentum inversion is extended non-trivially, so T to minus T in the notation that I used. Second remark, we have actually determined precise bounds. In the second step, this is for this is just the way the proof works out. In the second step, we establish precise bounds in order for this to be true. They depend on S, and I'm not giving them here, but they are in this paper that we posted a number of months ago. You get the Kitaev periodic table by taking for M the D-sphere. Yeah? So let me emphasize, we are happy with this result because it's true for a rather general momentum space. It's also true for torus or more exotic momentum spaces that we could imagine. So if we specialize to the D-sphere, then the suspension is another sphere in D plus one dimension, and we get the Kitaev periodic table as a corollary. So my time is up. This is my final slide. Maybe I can spend half a minute on this. So this is part of the proof strategy. It may be possible to use some direct argument, ignoring the work of Bott and focusing straight away on the diagonal map. For historical reasons, we did not try this. The strategy, by the way, that most of this is at the idea level and also at the level of working out proofs is due to Ricardo Kennedy, a PhD student who recently finished. So early on, Ricardo decided that we were going to relate this or reduce it to Bott's result. And the way this works is there is a certain vibration which is depicted here. There's a vibration which this is the fiber, this is the base, and the total space is the complex classifying space. There's a vibration which somehow maps everything onto the green part, and on the green part it squares. Yeah, so P is a square, and unfortunate thing which makes the proof longer, causes extra work, is that this vibration exists only in 2 out of 8 cases. For s equals 2 and s equals 6, one has this wonderful vibration, which means that we really have an isomorphism here. And then we can use the fact that the Bott map is highly connected in the language of homotopy theory. If the Bott map is highly connected, then this map is highly connected, and then by something called the Z2-Whitehead theorem, we get the desired result. So this is basically how it works in 2 cases, and for the other cases, we have to work some more. In particular, we have to use an easier bijection on the left-hand side, which comes directly from Bott's result, to establish the right-hand side for all values of S. All right, time is up. Let me repeat that what we have done in Cologne is a homotopy theoretic proof of the Kitaev table. We actually propose to call it the Bott-Kitaev table. I think this is what it should be called. Yeah? So it's my proposal, Bott-Kitaev table. We have given a proof by homotopy theory. The band number here is always kept finite or even small, and in doing so, one outcome is that we can say exactly what is the range where the K-theory calculation gives you the right answer. It turns out that outside the stability regime of K-theory, there, even in low dimension, there are some cases where homotopy classes are non-trivial. So in S equals 4, that's class C. These are spin singlet superconductors of broken time reversal symmetry. In 3 dimensions, one expects there's a set 2 invariant, so there should exist something that we call the Hopf superconductor. Anyway, this is a workshop on future directions of non-commutative geometry. What's not on this slide but should be on here is that this is done under the assumption that momentum is conserved. Real systems in real nature have some disorder, little or not so little disorder. So one needs to develop a better theory that does not rely on conservation of momentum. And the right framework to use for this is the framework of non-commutative geometry in the sense of Alain Kohn. That's, I guess, why I'm speaking here. And this is sort of my final sentence for this talk. And you will hear about this, I believe, from Hermann Schulz, or some aspects thereof. The beginning of this emerging work using non-commutative geometry, you will hear about from Hermann Schulz-Waldes tomorrow, I believe. Yes? So you take a specific ground state. That's a superconductor. Physically, it has spin-triplet pairing, and it is T-invariant. And you apply the diagonal map to that ground state. Then, going through this calculation, sort of an explicit expression here. Then you get a ground state in 2 dimensions with 2 symmetries. The doubling of 1-1 periodicity, he has a very physical meaning. It is you have to introduce band space. The superconductor doesn't need bands other than the spin. You know, there's spin triplet pairing and there's T, so you only have spin. Here, this doubling of number of bands means introduce 1 valence and 1 conduction band. This is the setting, the minimal setting where you can expect the non-trivial invariant. And then you get a concrete expression for the ground state. Yeah, so this map is not surjective at the level of ground state. It cannot be, because you always start with a vector bundle over a d-dimensional space, and by a very specific prescription, you're producing a vector bundle in 1 more dimension with 1 more symmetry. You're not going to get every possible vector bundle in the high dimensional space. However, what we prove is that you capture all the homotopy classes. You capture at least 1 in the various homotopy classes that you have. And it turns out that what you get is a particularly nice one. Is particularly symmetric. So to have a non-trivial class, the Kane-Meili Pfaffchen should have 2 zeros. In this case, these 2 zeros are located at pole and antipode of the 2-sphere. So it's a particularly aesthetically appealing representative of the quantum spin Hall class that you get. You could then try to randomize something, but the diagonal map gives you sort of the most beautiful representative. Who's there? Yes. Well, I guess I'm on record here. Whatever I'm going to say now will come back to hurt me. Maybe if you turn off the microphone, I'll give you my private answer. But seriously, I think, so let me try to give you a reasonable answer that can also be communicated over the ether. When it gets to this level, I think people point at Kitaev. Well, they say Kitaev said it. It's just God has spoken. But seriously, physicists have learned what is a Chern character and related. So they have learned what is a differential form, and that when you integrate the closed form, you get an invariant. So it's not necessary to have the full-fledged arsenal of topological weapons to figure out some partial answers. I think this is what physicists originally did. And then some of them are very ingenious. So I think this is quite brilliant. This was figured out by Kane-Meili, 2 physicists. They came up with this. They didn't write it in this language. I sort of polished it and sort of emphasized sort of the true mathematical structure, at least as I see it. But in their own words, saying it's called the overlap matrix, the matrix of overlaps formed with the T operator, they came up with this characterization. So it's proper to call it Kane-Meili, I would say. So short answer, particular results can be obtained by particular methods. If you want the grand picture, then you have to give reverence to Alexei Kitaev, who was the first to understand this. Well, the Majorana is in the picture. it's not among my examples. Let's see, where should I go? So when you hear about the Majorana, then this is this case. We are in one dimension, yeah, so it's called the Majorana chain. Somehow we are dealing with a one-dimensional superconductor with all symmetries broken. Yeah? So you break T by applying a magnetic field. You break spin rotations by having strong spin-orbit scattering. You break all the symmetries, and then and you do this in one dimension. And then by if the chain is Majorana, if it's topologically non-trivial, if we are in the non-trivial class here, there's a trivial class which you're not interested in, at least not for quantum computing. There's a non-trivial class here. If you are in that one, then by this principle called the bulk boundary correspondence, there are these special modes at the ends. You know, the boundary of a one-dimensional system are the 2 points at the end of the 1D system. There's a pair. They somehow really belong together. Something has fractionalized. Some electron has been fractionalized in a pair of Majoranas sitting at the ends. And physicists are very optimistic that you can use, and making concrete proposals to use this for quantum computation.
Okay, the organizer can let me go over.
So on the right-hand side, you have some physical materials that have actually been built, right, to illustrate the... So these are known cases. The quantum Hall effect has been known for a long time. A driving force of the whole thing was this case, which I selected for an example. It was, within a year or two, it was realized by essentially the same authors, Kane, Meili, Fu, that if you go up in one dimension from 2D to 3D, you still have a C2. Let's see. So now we are here, yeah? We stay in the same symmetry class. Strong spin-orbit scattering, but time reversal is preserved. We go up in dimension. We still have a C2 invariant. It's not directly related to this, but still a C2 invariant. There are experiments on this. Majorana has been mentioned. The one insight from this was that helium-3 in the B phase, which has been around for a long time, books have been written about it. The insight was that, we should also see this as a topological, superfluid. Yeah? One thing I never said is how come that insulators and superconductors are mentioned at once? A superconductor, isn't that the exact opposite of an insulator? Well, it is in the sense of charge transport. But instead of looking at charge transport, we could ask, how about spin transport or thermal transport? So a superconductor shunts electric charge transport, but if it's a spin singlet superconductor, it's an insulator for spin transport. And even if the spin rotation symmetry is broken, it is still an insulator for thermal transport. Yeah? So in that sense, helium-3 doesn't have a charge, so you can't talk about a conductance or such a thing, but you can, if you wish, talk about the thermal transport. And the prediction is there's something interesting happening at the surface of a bottle with helium-3 in the B phase. And I believe that people are even trying to do some experiments to verify whether reality conforms to a theoretical prediction.